This video is for section 6.3 binomial and geometric random variables. What do the following scenarios have in common? Toss a coin 5 times, count the number of heads, spin a roulette wheel 8 times, record how many times the ball lands in the red slot, take a random sample of 100 babies born in U.S. hospitals today, count the number of females. In each case, we're performing repeated trials of the same chance process. The number of trials is fixed in advance. In addition, the outcome of one trial has no effect on the outcome of the other trial. That is, the trials are independent. We're interested in the number of times that a specific event, we'll call it a success, occurs. Our chances of getting a success are the same on each trial. When these conditions are met, we have a binomial setting. So the definition of a binomial setting says that it arises when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. The 4 conditions for a binomial setting are binary. The possible outcomes of each trial can be classified as a success or a failure. Independent. Trials must be independent. That is, knowing the result of one trial must not have any effect on the result of any other trial. Number. The number of trials N of the chance process must be fixed in advance, and success. On each trial, the probability P of success must be the same. So, the way you can remember that is bins. So, binary, independent, number, success. And these are the things that you need to check for in order for you to have a binomial setting. The count X of successes in a binomial setting is a binomial random variable. The probability distribution of X is a binomial distribution with parameters N and P, where N is the number of trials of the chance process and P is the probability of a success on any one trial. The possible values of X are whole numbers from 0 to N. So let's try an example. So here are 3 scenarios involving chance behavior. In each case, determine whether the given random variable has a binomial distribution and classify your answer, or justify your answer. So on A, it says that genetics say that children receive genes from each of their parents independently. Each child of a particular pair of parents has a probability 0.25 of having type O blood. Suppose these parents have 5 children. Let X equal the number of children with type O blood. Alright, so in order for us to check and see if they would have a binomial distribution, we have to go through bins. And so for A, the first one is binary. And so do we have either success or failure? And so we could say, because it's asking us about children with type O blood, then a success would be type O, and a failure would equal not type O. The next one is independent. So does one child having type O blood affect the probability of the next child having type O blood? And because we're talking about, it tells us in our problem that children receive genes from their parents independently. So this is a yes. The next one is number. So that just means that we have a set number of trials that we're looking at. And so it tells us in our problem that we're looking at 5 children, so our number is set to 5. And the last one is success. So do we have the probability that we're successful? And that would be what we let be, what it says here. So it says probability 0.2 of having type O blood. 2.5 having type O blood. I'm struggling today. Alright, so because we could answer all of these questions, then that means that we do have a binomial setting. Since x equals the number of successes, it is a binomial random variable with parameters n equals 5 and p equals 0.25. So for this one, our n would equal 5. That's the number of people that we're looking at. And our p would be the probability that we're successful. We said that to be successful, it meant to have type O blood. And we know that the probability of having type O blood from our problem is 0.25. Alright, so for the next one, shuffle a deck of cards, turn over the first 10 cards, one at a time, let y equal the number of aces you observe. So the first question is this binary? So do we have a success or a failure? So our success for this one, because we want it to be the number of aces that we observe, is going to be number of aces. Really, it's not really the number of aces as much as it is getting an ace. So a failure would equal not getting an ace. Independent, so does one affect the other? That's not independent. Beyonce would be very upset. So think about whenever you're shuffling a deck, you're turning over the first 10 cards. Each card that you turn over, even though you drew all of those 10 cards at one time, is going to depend on what happened with the first card because you're not replacing that card that you took. So these are not independent. So this is a no. For example, if the first card you turn over is an ace, the next card is less likely to be an ace because you're not replacing the top card in the deck. Similarly, if the first card isn't an ace, the second card is more likely to be an ace because you didn't replace that first card. The second thing is a number. So do we have a set number of trials? And this one, yeah, we do have a set number of trials. It's n equals 10. But we don't have a number of successes. And because we said no to this independent, it's automatically not a binomial setting. So you have to be able to satisfy all of those, all 4 of those questions. So let's look at C. Shuffle a deck of cards, turn over the top card, put the card back in the deck, and shuffle again. Repeat this process until you get an ace. Let W equal the number of cards required. So for this one, our binary question would be, again, success is an ace, failure is not an ace. Independent. This one would be independent because we are replacing those cards every time. So when we replace, it doesn't change the likelihood of the next card being an ace or not being an ace. So this one would be independent. Number, do we have a set number? So it says that the number of trials is not set in advance. So we don't have like for sure we're choosing this many cards. You could get an ace on the first card you turn over, or it may take many cards to get an ace. Because there's no fixed number of trials, this is not a binomial setting. So again, this is not a binomial setting. Check your understanding. For each of the following situations, determine whether the given random variable has a binomial distribution. Justify your answer. So for number 1, it says shuffle a deck of cards, turn over the top card, put the card back in the deck, and shuffle again. Repeat this process 10 times. Let x equal the number of aces you observe. Alright, so for number 1, you're going to have to go through bins. So the first thing is binary. So what is your success and what is your failure? So a success for this one would be getting an ace. A failure would be not getting an ace. The next question is independent. So does one affect the other? And because it tells us that we are putting this card back in the deck, then that means that what happens with the first one does not affect the second one, and so on and so forth. So it is independent. That's good. N is for number. So do we have a set number of times that we're doing this? And in our problem, it tells us that we are choosing 10 cards. So our number would be N equals 10. And the last one is success. So do we know the probability that we get a success? And so we can figure out what the probability is because we know that there are 4 aces in a deck of 52 cards. So the probability that you get a success would be 4 out of 52. Which would be 0.08. So we can say that yes, this is a binomial setting. And what we know about that binomial setting is that n is equal to 10 and that the probability is equal to 4 out of 52, or you could also say 0.08. To choose 3 students at random from your class, let y equal the number who are over 6 feet tall. So again, we're going to go through bins because we're trying to see if we have a binomial distribution. And so the first one is binary, and so we need to know what is a success and what is a failure. So because we are looking at the number of students who are over 6 feet tall, then a success would be over 6 feet. A failure would be not over 6 feet or shorter than 6 feet. The next one is independent. So does one affect the other? So if you think about this, if we choose a student from class and that person is over 6 feet tall, then the number of people who are, the probability that the next person is over 6 feet tall just went down because we're not putting that person back in our stack to choose from. So once we have a person, then that person does not go back into the class so that we can choose from them again. We wouldn't choose that same person all 3 times. So this would be not independent. And because we couldn't answer that this was independent, we failed to answer all 4 questions, and that means that this is not a binomial setting. Three, flip a coin. If it's heads, roll a 6-sided die. If it's tails, roll an 8-sided die. Repeat this process 5 times. Let W equal the number of fives that you roll. Alright, so we're going to start with binary. So can we say what a success is and what a failure is? So for this one, a success would equal getting a 5. like rolling a 5. And a failure would be not a 5. The next one is independent. So does what we do with one affect the other? Because we are rolling a die, then what we get on the first number is not going to affect what we get the second time. So these are independent. Then we should look at numbers. So do we have a set number of trials that we're going to look at? And it tells us that we're going to repeat this process 5 times. So that means that our n is equal to 5. And then we have to look at success. So can we say what the probability of getting a 5 is going to be? And so because we know that we are using either a 6-sided die or an 8-sided die, then we can't determine the probability of the success because it's going to change every time. So we don't know what that is, and because we don't know what the probability that the success is going to be, we say it's not a binomial setting because we have to be able to answer all 4 of those questions to be able to say that we have a binomial distribution. So we're going to talk about a binomial coefficient next, and that's the number of ways of arranging k successes among n observations. And so we have this n over k in parentheses, and we show that it's equal to n factorial over k factorial times n minus k factorial. Remember that the factorial means that we multiply all the way down, and it looks like an exclamation mark. But if I had like 3 factorial, that would mean 3 times 2 times 1. If I had 6 factorial, it would equal 6 times 5 times 4 times 3 times 2 times 1. So you basically start with whatever number they give you, and you multiply every single number all the way down until you get to 1. There is a button on your calculator that will do a factorial. And that is, like if I wanted to know what 6 factorial was, I would type in 6, and then I would go to math. I would go to PROB, which stands for probability, and go to option 4, which it looks like the factorial, or the looks like an exclamation mark, and then I would get 720. So the calculator will do that for you, so you don't have to work it out.
We need Rickeya Gray to report Miss Aldrin at this time. Rickeya Gray, please report Miss Aldrin.
All right. So this will also be done. You can also do this on the calculator. And the good news is you have maybe done a binomial coefficient before. So this formula here is also used for a combination. And so a long time ago, maybe when you were in another previous class, you learned about permutations and combinations. Permutations being where the order that you do things matters, and combinations being the order that you do things does not matter. So for example, if I was putting everybody in this class in order, not a specific order, just an order, I would use a combination. If I was choosing from this class 4 people, and they weren't the 4 best people, or the 4 people that were the tallest or had the highest grades or whatever, they were just 4 random people, then I would use a combination. You can do this on a calculator. So like if I was doing 5 over 2, that would mean that I had 5 things, and I was choosing 2 of them. So 5 being n being my number of things that I have, and k being the number that I'm choosing. And so I can do this on the calculator by typing in 5 first, going to math, going to PROB, and going to NCR. So the N stands for the number that I have. The C stands for a combination, which in this case you're going to be doing binomial coefficients. So you might want to think about the C standing for maybe coefficient, and the R standing for the number of things that I'm choosing. So I'm going to go with 3, and then I'm going to type in the number that I'm choosing, and we said that we were going to choose 2. And so once I get that typed in, I just hit enter, and it gives me 10. What that means is there are 10 different ways that I can pick 2 people from 5. Binomial probability. So if X has a binomial distribution with n trials and a probability P of success on each trial, the possible values of X are 0, 1, 2, all the way to n. If K is any one of these values, then P equals X, or P probability of X equals K equals n over K times P to the K times 1 minus P to the n minus K. That looks like an awful mess. But remember that your N is your total number of trials, that your K is the trials that you're specifically looking at, or the numbers that you're specifically looking at from that trial, and then your P is the probability that K happens. So using the binomial probability formula, each child of a particular pair of parents has a 0.25 probability of having type O blood. Suppose the parents have 5 children. A says find the probability that exactly 3 of the children have type O blood. So for A, we want to know the probability that X equals 3. So to do that, we would say we have 5, we're looking at 3 of them. The probability that a child has type O blood is 0.25. We're going to raise that to the 3rd power because that's how many people we're worried about. There's a 0.75 chance that they do not have type O blood. And there's 2 from the 5 that wouldn't have type O blood based on our scenario here. Now, all of this came from this formula. So N was the number that I had, which we said was 5. K was the number that I'm worried about being a success, which we said was 3. The probability that we have a success was the 0.25, which is the probability of having type O blood. The K represented the 3, because that's how many people we were looking at having type O blood. We do 1 minus the probability, so 1 minus the 0.025, which gave us the 0.75. And then we do N minus K, so we do 5 minus the 3, which gives us 2. This part we do the NCR thing, so on our calculator, we would do 5, go to math, go to probability, go to NCR, which is 3, and we were looking at 3. So there is 10 different ways I can make that happen. So this is going to be 10. Then I have to do 0.25 to the 3rd. Actually, let's do this. It may make it a little easier. So let's say 10 times 0.25 to the 3rd times 0.75 to the 2nd. And when we do that, we would get 0.08789. Actually, we can do this. Let me just write this. And so when we work that out, 0.08789. So the probability that exactly 3 out of 5 have type O blood would be 0.08789. B. Should the parents be surprised if more than 3 of their children have type O blood? Justify your answer. So what we are doing for this one is the probability that X is greater than 3. And so if we think about being greater than 3, there's only 5 children, so that means the probability that x is equal to 4 plus the probability that x is equal to 5. We can find all the information that we need about the probability that x is equal to 4 by saying 5, choose 4, 0.25 to the 4 times 0.75 to the 1 plus 5, choose 5, times 0.25 to the 5th times 0.75 to the 0. So on our calculators, we could say, parenthesis, 5, math, NPR, or NCR, 4. Times 0.25 to the 4th times 0.75 to the 1st plus, parenthesis, 5 math, PROB, NCR, 5, 0.25 to the 5th times 0.75 to the 0. And for that, we would get 0.015625. There is a faster way to do that. And so if we wanted to do that the faster way, we could use something on our calculator called binomial PDF, binomial CDF. So if it's equals, you would do binomial PDF, with n being the number of trials that you have, or the number total, p being the probability, and k being the number that you're looking at. And for like a less than or equal to, you would do CDF. So if we wanted to start out by finding x equals 3 using our fancy calculator tools, then we could go to our calculator. We would go to second vars. You are going to scroll down. You're going to get past all the numbers. And because it's x equals 3, we've got to do binomial PDF. So we hit this one. Our trials is 5. Our probability is 0.25. X value is 3. And so whenever we do that, we get 0.08789, which is what we got the first time when we worked the first part of that problem out. To find P is greater than 3, so if you think about P is greater than 3, if you're thinking about the successes that you have, P is greater than 3 would be the 4 and the 5. So basically, I know that 1 in this case is going to represent not this one, but the whole entire thing. So basically like 100%. So if I can subtract out when P is less than or equal to 3, and I want to do that because that's the normal that's the binomial CDF. That's the only time I can use that, is if it's less than or equal to. So I can subtract out the stuff that's less than or equal to 3, then I can get the 4 and the 5 to kind of be isolated. So to do that one, I would say 1 minus second vars. Go through this list until you get down to the letters, and it should be B. And you can also do alpha and then B, and that should take you there as well. So binomial CDF trials would be 5, probability would be 0.25, X value would be 3, and then paste. and we would get 0.015625, which is essentially what we got when we worked at the last one. Of course, you could have also done this as probability is greater than 3, and saying x equals 4 plus x equals 5, and doing binomial PDF with 4, binomial PDF with 5, and then adding them together to get your answer. Check your understanding. To introduce her class to a binomial distribution, Mrs. Desai gives a 10-item multiple choice quiz. The catch is students must simply guess and answer A through E for each question. Miss whoever uses her computer's random number generator to produce the answer key so that each possible answer has an equal chance to be chosen. Patty is one of the students in the class. Let X equal the number of Patty's correct guesses. So the first thing we have to do is show that X is a binomial random variable. So the way that we do that is we have to check bins. So we start with, is this binary? Can I say what the success equals and what the failure equals? So a success is correct guess, and a failure would be an incorrect. Independent, so does one affect the other? And so yes, this would be independent. Because the random number generator is choosing which numbers are going to be, which answers are going to be correct number. So are there a set number of questions that we're looking at? And that's true. We have n equals 10. And the last one is success. So do we know what the probability that she had a correct guess was? So because she's got A through E, that's 5. And if she has 5, then that means that each one of them would have a 20% chance of being correct. Because, of course, all 5 of them, if I was doing this as an OR, would all add up to be 100. So each one separately would have a 20% chance of being correct. The second thing is to find the probability that X equals 3. You're all standing out in the hall, and I'm going to leave you there for a minute. So the probability that X equals 3. So this would be equal to, you could work that all out and get your big long formula, or you could go on your calculator, and because it's equals, you would do a PDF. So you would say second vars. You would go to alpha A because that's going to get you to binomial PDF. Your number of trials would be 10. Your probability would be 0.20. Your X value is 3. And whenever you work that out, you would get 0.2013. For question 3, it says, to get a passing score on the quiz, a student must guess correctly at least 6 times. Would you be surprised if Patty earned a passing score? Compute an appropriate probability to support your answer. And so if we were doing number 3, what we would need to do is find the probability that X was greater than or equal to 6, which means that she can get 6 and anything all the way up to the number of questions that she has, which is 10. So we would start by saying probability that X is equal to 6 plus the probability X is equal to 7 plus the probability X is equal to 8 plus the probability X equals 9 plus probability X is equal to 10. So the easiest way to do that, because each of these are equal to, the easiest way to do that is binomial PDF. So we would go on our calculator and we would go to second vars. We would go to alpha A because it is the binomial PDF. Our number of trials would be 10. Our p-value we determined would be 0.20. Our x value would be 6 to start with, and then we would add to that second vars, alpha A. Trials would be 10, p-value would be 0.20 still, x value would change to 7. Keep going, so we would need to do 8, second vars, alpha A. Everything stays except for the x value, which changes to 8. Second vars, alpha A. Everything stays except the x value, which changes to 9. And last one, second vars, alpha A. Everything stays except for the x value, which changes to 10. When we do that, we get 0.00636938824, which would round and be approximately 0.006, which if we moved our decimal 2 places would be 0.6%. And so the question asked us is, would we be surprised if she passed the test? And so it says there's only a 0.64% chance that a student would pass. So we would be quite surprised if Patty was able to pass the quiz. Mean and standard deviation of a binomial random variable. If a count x has a binomial distribution with a number of trials n and a probability of success p, the mean and the standard deviation of x are, the mean of x would be equal to the number of trials times the probability, and the standard deviation of x would be equal to the square root of the number of trials times the probability times 1 minus the probability. So on an example, Mr. Bullard's AP Statistics class did the activity on page 340, which is basically looking at bottled water versus tap water. It says there are 21 students in the class. If we assume that the students in his class cannot tell tap water from bottled water, then each one is basically guessing. And so it says that each of them basically have a 1/3 chance of being correct. We let x equal the number of students who correctly identify the cup containing the different type of water. The first thing we have to do for A is explain why x is a binomial random variable. And so for A, we would go through our bins again. So we would check on B, which stands for binary. So remember, with binary, we are basically looking to see if we have two things that we are talking about. And so one of them is a success, one of them is a failure. So a success would be the correct identification. So between, is it bottled water, is it tap water? And a failure would equal an incorrect identification. I stands for independent. So does one affect the other? And so it says one student's result should have no effect on another student's result. Because if one student identifies the water correctly as tap water, it does not affect what happens with the second person. So they are independent. The next one is number. So do we know the number of trials that we're looking at? And it tells us there are 21 students in the trial, which means that there are 21 people that we're looking at. And the last one is success. So do we know what the success rate is? And because it tells us that they have a 1/3 chance of being correct, then we know what P is equal to. And we know that it's equal to 1/3, or you could say 0.33. The second part of that asks us to find the mean and the standard deviation of x and interpret each value in context. So using what we just had on the last page, our rules for mean and the standard deviation of a binomial random variable, to find the mean value of x, then we would say the number of trials times the probability. So the number of trials being 21, the probability being 1/3. And so if we do 21 times 0.33, we would get 6.93, which is approximately 7. So what that means is that we would expect about 1/3 of the, Mr. Bullard's students, the 21 students, to guess correctly. So that's about 7 students to guess correctly. We could also find the standard deviation for x by using the square root of np times 1 minus p. And so that would be the square root. np we already determined was going to be 7 times 1 minus 1/3. So that would be the square root of 7 times 2/3. And whenever you work out the square root of 7 times 2/3, you would get 2.16. And so what that means in context is if the activity were repeated many times with a group of 21 students who were guessing, the number of correct identifications would differ from 7 by about an average of 2.16. So you're looking at approximately on each trial between 5 and 9 students getting the correct identification. C says, of the 21 students in the class, 13 made correct identifications. Are you convinced that Mr. Bullard's students can tell bottled water from tap water? Justify your answer. So what we're looking at on letter C is we're saying that the probability that X, which is the number of students who get a correct identification, is greater than or equal to 13. And so basically, if we're doing that, we can say the whole class would be 1, and we would subtract out the probability that less than or equal to 12 students get the correct identification. So we can identify, the reason we would change it into this is because we have a function on our calculator that tells us about less than or equal to. And so we could go on our calculator, and we could say 1 minus, because it's a less than or equal to, we would do second vars. This time we would do alpha b, because alpha b would give us binomial CDF. Our number of trials would be 21. We said that our probability would be 0.33, or approximately 1/3, and we're looking at x values that are 12 or less. So then we could do 1 minus all of that, and we would get 0.0068. And so basically what that means is the students have less than 1% chance of getting so many right if they are just guessing. So this is a strong evidence that some students in the class can tell bottled water from tap water. So check your understanding. Refer to the previous check your understanding on page 390 about Mrs. Desai's special multiple choice quiz on binomial distribution. So this is kind of the same check your understanding question that we talked about before. And we want to define x is equal to the number of Patty's correct guesses. So the first thing we have to do is find the mean of x. And so if we look back at that last check your understanding that we had, it says, to introduce her class to binomial distributions, Mrs. Desai gave a 10-item multiple choice quiz. The catch is students must simply guess and answer A through F for each question. Mrs. Desai uses her computer's random number generator to produce the answer key so that each possible answer has an equal chance of being chosen. Patty is one of the students in this class. Let X equal the number of Patty's correct guesses. So if we're finding the mean of x for this one, we're going to use n times p. And so the n would be equal to the number of trials that we have, which in this case is going to be 10 because it was a 10-question test. And then we said that the probability was 0.20. And so we can find 10 times 0.20 by going to a calculator, and of course it would give us 2. And so that means that the mean for the Mrs. Say special multiple choice quiz on binomial distributions would be 2. So approximately, on average, we would expect the students to get 2 answers correct on this quiz. 2 asks us to identify the standard deviation and interpret this value in context. So to find the standard deviation for x, we would have to use the formula n times p minus 1 minus p, or times 1 minus p. And so we know that n times p is going to be 2. We know that 1 minus p would be 1 minus 2, which turns out to be the square root of 2 times 0.8. And so if we work that out, we would get 1.265. So we would expect individual students to score their scores to vary from a mean of 2 answers by an average of 1.265 correct answers. 3 says, what's the probability that the number of Patty's correct guesses is more than 2 standard deviations above the mean? Show your method. So the first thing we have to do is talk about what does it mean to be more than 2 standard deviations above the mean. So if we know that the mean is equal to 2, and we know that the standard deviation is equal to 1.265, then 2 standard deviations above the mean would be the mean plus 2 times 1.265. And so if we work that out, we would say 2 plus 2 plus 2 times 1.265 would equal 4.53. So basically what we want to know is what is the probability that a student gets more than or equal to 4.53. And technically, I don't think it would actually be equal to, it would just be more than 4.53. And so the way we could do that is we could say, well, what is the probability that we're looking at 1 minus, the whole entire class minus x being less than or equal to 4. Let's just say 4. So 1 minus the probability x is less than or equal to 4. And the reason that we go with 4 is because obviously you can't get 4 and a half. So you can't get 4 and a half questions right. You either get them right or you get them wrong. So if we can say what is the probability that they are less than 4, then we can figure all of that out. Or 4 or less. And so on our calculator, remember that because we did a less than or equal to, we can use the function on our calculator to do that. So we would say 1 minus second vars, because we are looking at a less than or equal to, we can do alpha b to get the binomial CDF. Our number of trials would be 10. We said our probability was going to be 0.20, and our x value for this one is going to be 4. And so whenever we do that on our calculator, we would get 0.0328. Sampling without replacement condition. When taking a simple random sample of size n from a population of size capital N, so the capital N represents the population, the lowercase n represents the sample from that population, we can use a binomial distribution to model the count of successes in the sample as long as the number that we are taking from the sample is less than or equal to 1/10 of the entire population. So when we look at an example about that, we've talked about this hiring discrimination example before. We did that at the very beginning of the year. And so just to remind you what that is, an airline has just finished training 25 first officers, 15 male and 10 female, to become captains. Unfortunately, only 8 captain positions are available right now. Airline managers decide to use a lottery to determine which pilots will fill the available positions. Of the 8 captains chosen, 5 are female and 3 are male. Explain why the probability that 5 female pilots are chosen in a fair lottery is not the probability x equals 5, which is equal to 8 total. You're choosing 5. The probability that you choose a female, which is the success that we are looking for because we're talking about 5 female pilots, would be 10 out of 25, which if you do 10 out of 25, you would get 0.40, so that's where the 0.40 comes from. To the 5th, because there are 5 females that we're talking about, which means that 60% would be left over, and there are 3 males that would make up that 60%, and that gives us 0.124. And so it says the correct probability is 0.106, and it is important to recognize that this is a binomial that we talked about earlier, so this is a binomial formula. And it's also important to note that what's happening in the lottery is we would be like, if we started from the beginning and we were doing a lottery, we would choose a person, and when we read that person's name, we would set that person's name aside, and we wouldn't put that name back in the pot to be chosen from again, which means that each of the draws are going to be dependent on what the first one was. So while it is true that at the beginning there's a 40% chance that the person that you choose is female, on the next draw, if we assume that the first draw was a female, then the number of females that are possible on the second draw would be less because we keep out the first female that we drew, which means that the probability is going to change from 0.40 to whatever it would be if now we only had 9 females out of a total of 24 people. So if we did that, we would see that on the second draw, our probability of choosing a female then goes down to 0.375. And so with a binomial formula, that's okay. We can do that anytime we have independent situations. But because in this situation it's very obvious that it's dependent because we wouldn't be replacing that female's name, we can't use a binomial formula. It's also important to note that based on what we talked about with this condition here, sampling without replacement, we have to have our sample, which is the number that we're choosing, and it has to be less than or equal to 1/10 of the entire population, and so N would be our population. So we have to have this condition here, and so the number that we are choosing would be 5, and so we need that 5 to be less than or equal to 1/10 of the total number, which is 25. And so if we do that, we would see 1/10 of 25 is going to be 2.5. And so 5 is not less than or equal to 2.5, which means that this is not true. Normal approximation for binomial distribution. Suppose that a count X has a binomial distribution with n trials and the success probability P. When n is large, the distribution of X is approximately normal, with the mean mu sub X equal to the number of trials times the probability, and a standard deviation, sigma sub X equal to the square root of the trials times the probability times 1 minus the probability. Both of these are what the rules that we discussed earlier. As a rule of thumb, we will use the normal approximation when n is so large that the number of trials times the probability is greater than or equal to 10, and the number of trials times 1 minus the probability is greater than or equal to 10. That is that the expected number of successes and failures are both at least 10. Survey sample shows that fewer people enjoy shopping than in the past. A survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed that I like buying new clothing, but shopping is often frustrating and time-consuming. The population that the poll wants to draw conclusions about is the U.S. residents aged 18 and over. So the problem is we're going to suppose that exactly 60% of adult U.S. residents would say agree if asked the same question, and we're going to let X equal the number of the number in the sample who agree. So in part A, we need to show that x is approximately a binomial random variable. So to start with A, we have to check for bins. So B stands for binary, so we have to say, are there two things that are happening? Can we label them as success and failure? And so for this one, success would be agree, and failure would be disagree. For I, that would be independent. And so does what one person says affect what the second person says? And so because there are 235 million adults in the United States, the responses of the 2,500 randomly chosen adults are very close to independent. So this would be a yes. The second is number. So do we know how many people that we're talking to? And so our number of people that we're talking to, or in this case our trials, would be equal to the 2,500 people that are shopping in the mall. And success, which is the last thing that we have to choose or have to look at for a binomial random variable, is basically what is the probability. Does it tell us the probability that we have a success, which is people that agree? And so we are going to suppose that exactly 60% of all adult U.S. residents would say agree. So for this one, our probability is going to be equal to 0.60. Because all of those conditions were satisfied, then that means that we do have a binomial random variable. So for B, it asks to check the conditions for using a normal approximation in this setting. So on the last little bit that we talked about, what we would do is we would check out what our mean would be and what our standard deviation would be, and we have to make sure that both of those would be greater than or equal to 10. And so we are going to use our n and our p to do that. And so we're going to start with finding the mean of x, which would be n times p. And so we would do 2,500 times 0.60. And so basically, what is 60% of 2,500? And that would be 1,500. So obviously, n times p is greater than or equal to 10 is one thing that we need to show, and obviously that would be 1,500, and 1,500 is definitely greater than 10. The next thing that we need to look at for a normal approximation in this setting would be to check out what is happening when we say the number of trials that we're looking at times 1 minus p. And we want that to be greater than or equal to 10 as well. So we know that the number of trials that we're looking at is 2,500, and we can figure out that 1 minus p is 0.6, where p is 0.6 would be 0.4. So basically we're finding 40% of 2,500. So when we do that, we would find that it's 1,000, and 1,000 is definitely greater than or equal to 10. Because we were able to satisfy both of those requirements, then that means that we should be safe to use the normal approximation for this problem. So then looking at C says use a normal distribution to estimate the probability that 1,520 or more of the sample agree. So basically we are trying to find the probability that x is greater than or equal to 1,520. So what we are going to do is we could, for this, we could use the standard normal table. We could say that we have to first find our z, And remember, in order to find our z-square, we would say our observation minus our mean over our standard deviation. So we need to find what our mean is, and we also need to find what our standard deviation is. We already know that our mean is 1,500. We were able to find that up above. And so then we need to find our standard deviation for x. And to find our standard deviation for x, we would say the square root of np times 1 minus p. And that was from a rule that we talked about earlier in the notes. And so we would find the square root of the n times p is what we did for the standard deviation, so that would be 1,500. And then we're doing 1 minus 0.6, which we already said was 0.4. So we're doing the square root of 1,500 times 0.4. And when we do that, we get 24.49. So we would find our z by saying our observation, which is 1520, minus 1,500, which is our mean, over our standard deviation, which is 24.49. Whenever we do that, we would find that our z-score is 0.82. So if we're finding the probability that x is greater than or equal to 1520, that means that we're really finding the probability that z is greater than or equal to 0.82. And so we could look on our standard normal table, and whenever we do that, let me see if I can find one real fast. Alright, so whenever we do that, because we are saying greater than or equal to, remember the standard normal table tells us about less than, and so we're going to say 1 minus whatever our table tells us about 0.82. So if I go back to the table and I go to 0.8 and then over to 0.02, I would see that it's 0.7939. So 1 minus 0.7939. And whenever we work that out, we find that the probability that x is greater than or equal to 1520 would be 0.2061. Alright, so I'm going to set up this activity, the birthday game, and then you'll see that again later in an example that's coming up. So it says your teacher is planning to give you 10 problems for homework. As an alternative, you can agree to play the birthday game. Here's how it works. A student will be selected at random from your class and asked to guess the day of the week, for instance Thursday, on which one of your teacher's friends was born. If the student guesses correctly, then the class will have only one homework problem. If the student guesses the wrong day of the week, your teacher will once again select a student from the class at random. The chosen student will try to guess the day of the week on which a different one of your teacher's friends was born. If this student gets it right, the class will have 2 homework problems. The game continues until a student correctly guesses the day on which one of your teacher's many friends was born. Your teacher will assign a number of homework problems that is equal to the total number of guesses made by members of your class. A geometric setting arises when we perform independent trials of the same chance process and record the number of trials until a particular outcome occurs. This is just like what we were talking about with the birthday problem. The 4 conditions for a geometric setting are binary, So the possible outcomes for each trial must be classified as success or failure, which we've been doing. Independent trials must be independent. That is, the result of one trial must not have any effect on the result of any other trial. We've been doing that. Trials, the goal is to count the number of trials until the first success occurs. And success on each trial, the probability P of success must be the same. So whenever you're doing a geometric setting, you're going to be doing bits instead of bins. The number of trials y that it takes to get a success in a geometric setting is a geometric random variable. The probability distribution of y is a geometric distribution with parameter p, the probability of success on any trial. The possible values of y are 1, 2, 3, and so on and so forth. So going back to the birthday game, the random variable of interest in this game, y, equals the number of guesses it takes to correctly match the birthday of one of your teacher's friends. Each guess is one trial of the binary process. Let's check for the conditions for a geometric setting. So the first one is binary. So remember, on a geometric setting, you're trying to look at bits instead of bins. So B stands for binary. So are you able to say what a success is and what a failure is? And so a success would be a correct guess and a failure would be an incorrect guess. Independent is what your I stands for, and so the result of one student's guess has no effect on the result of any other guess because each student is trying to guess a different person's birthday. Trials, we're counting the number of trials up to and including the first correct guess. And success is your S. On each trial, the probability of a correct guess is 1 out of 7. The reason it's 1 out of 7 is because, of course, you're trying to look at a day of the week, and there are 7 days of the week. And so the probability that that the day you chose is correct is 1 out of 7. This is a geometric setting because y counts the number of trials to get the first success. It is a geometric random variable with parameter p equal to 1 out of 7. Geometric probability. If y has a geometric distribution with probability p of success on each trial, the possible values of y are 1, 2, 3, and so on and so forth. If k is any one of these values, then the probability x is equal to k is equal to 1 minus the probability to the k minus 1 power all times p. So, calculating geometric probabilities. So what does this actually look like if we're working through a problem? So the first thing we have to do is find the probability that class receives 10 homework problems as a result of playing the birthday game. So for A, you are basically trying to find that the probability that that y is equal to 10. And so if you're finding the probability y is equal to 10, you're going to have to use this formula here. And so you would be saying 1 minus the probability to the k minus 1 times p. And so p, of course, is going to be our chance at success, which is 1/7. And our k is going to be equal to 10. And so we're doing 1 minus 1/7 to the 10 minus 1 all times 1/7. So 1 minus 1/7, of course, would be 6 out of 7, and 10 minus 1, of course, would be 9. So we're doing 6 out of 7 to the 9th power times 1/7. So on your calculator, you would do 6 out of 7 to the 9th power times 1/7. Whenever you do that, you get 0.0357. So the probability that the class receives 10 homework problems as a result of playing the birthday game would be approximately 0.04, which turns into 4%. B, find the probability that y is less than 10 and interpret this value in context. So if y was less than 10, we would say that that would mean the probability that y was equal to 1 plus probability that y was equal to 2 plus the probability y equals 3, and so on and so forth until we get to the probability y equals 9 and the probability that y equals 10. Now, you could work all of those out using the formula above. However, the faster way to do that is on your calculator. And so, to kind of spring forward a little bit, in your notes you'll see that the easier way to do it on the calculator is to use Geomet PDF and Geomet CDF. And so we use PDF if we have an equal situation. We use CDF if we have a less than or equal to situation. And so for our problem, we're doing less than. And so what we would need to do for that is we would basically say that P is less than or equal to 9. And the reason that we are able to do that, or P, the probability that Y is less than or equal to 9, and the reason that we're able to do that is because you're not going to be assigned a half or a portion of a question of a homework question. You're going to either be assigned 9 or assigned 10. And so we're able to say that the probability that Y is less than 10 would be the probability that it was 9 or less than that. And so doing that on the calculator, we're able to go to second vars, and then you would scroll down and you'll go past all the binomial stuff, and you'll keep going until you get to Geomet PDF, Geomet CDF. And so because you are doing a less than or equal to, you're going to do CDF. So PDF is for if it's an actually this Y is equal to this number, and a CDF is if you're talking about a less than or equal to. So our probability we said was going to be 1 out of 7th, or 1 out of 7, so 1/7, and our x value for this case is 9. And so whenever we do that, we would get 0.75, which turns out to be 75%. So what that means is there's about a 75% chance that the class will get less homework by playing the birthday game. And once again, these are your steps in order to be able to do it on the calculator. The mean or expected value of a geometric random variable. So if y is a geometric random variable with probability of success p on each trial, then its mean or expected value is equal to the mean of y, which is equal to 1 over p. That is the expected number of trials required to get the first success is 1 out of p. So check your understanding. Suppose you roll a pair of fair 6-sided die until you get doubles. Let t equal the number of rolls it takes. And the first thing we have to do is show that t is a geometric random variable, and we're basically going to be checking bits in order to do that. So the first thing we have to show is it binary? So do we have a success? And do we have a failure? So success would be rolling doubles. A failure would be not rolling doubles. Independent would mean does one roll affect the other? And so rolling dice is an independent process. Which means that what we roll on one die is not going to affect what we roll on the other die because they're two totally separate die altogether. The next thing we're going to talk about is trials. And so for the trials, we're counting trials up to and including the first success. And the last one is success. So can we say what P is equal to? And so the probability of success is going to be 1/6 for each roll. And the reason it's 1/6 is because there are 6 ways to get doubles out of a total of 36 possible rolls. And so because we are able to satisfy all of the conditions for bits, then we say that this is a geometric setting. Since x is measuring the number of trials to get the success, it is a geometric random variable with p equal to 1/6. So next we want to find the probability that t is equal to 3 and then interpret this result in context. If we're finding that p is equal to 3, we are able to do this because we said that this was a geometric random variable. We're able to do this on the calculator by going to second bars and then going to where we have geometric CDF and geometric PDF. And because we have an equals, we're able to use geometric PDF. So we're going to do geometric PDF. Our probability we said was going to be 1/6, and our x value that we are looking at is 3. So whenever we do that, we get 0.1157. Three says, in the game of Monopoly, a person can get out of jail free by rolling doubles within 3 turns. Find the probability that this happens. So what that means is that we're finding the probability that t is less than or equal to 3. Because we are doing a less than or equal to 3, we can do this on the calculator by saying 1 minus the probability that t is actually, we don't even have to do that part. Because it's less than or equal to 3, we're okay, and we can actually just do this on the calculator by going to the calculator, and this time, instead of using Geomet PDF, we're able to use Geomet CDF because it's a less than or equal to. So we would go on our second bars menu, and we would go to Geomet CDF. Our probability would be 1/6, again, because we're talking about rolling die, and the probability that we roll doubles out of 36 rolls would be 1/6. And we're looking at an x value of 3. And when we paste that, we would get our answer as 0.4212962,963. And so it's basically 0.4213.